Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to look at a second proof of the Pythagorean theorem. And this one is going to look very geometric. And the only thing it's really going to use is the decomposition property of areas and the fact that the area of a square is its side length squared. If you notice and have been paying attention, the diagram that I use for all of my cover pages to the lecture notes, those come from this proof. Without further ado, let's go ahead and prove it. I'm not going to restate the Pythagorean theorem, and I'm going to reuse the names of the sides little a, little b, and little c, just like we had before. So here we start with the right triangle ABC. And as a reminder, right, this is our hypotenuse here is C, is this distance here. And then these legs are little a and little b, respectively. So now I build a square of side a plus b, and I make sure that my triangle here is in the corner, and I've labeled the right angle, and I've labeled the angles that we have here, whatever they might be. And now what I do is I take a copy of this right triangle, or I should say 3 more copies, and I place them at each of the corners. And I made it so that, let's say this is side A, then I put side A here, and that's B. Here I have B, here I have A, here I have B, here I have A, and here I have B. And right, I've placed it in a square of side length A plus B. I can do that because I have right angles here, right? So because of these right angles, these fit snugly into the corner of my square. And now let's look at this white shape that I have in the middle there. So here's the little bit of magic, right? By the angle sum in Euclidean triangles, right, the angle here labeled with 1 tick mark and the one there labeled with 2 tick marks, together with the right angle, have to add up to 180 degrees, which means that the one with 1 tick mark and the one with 2 tick marks add up to 90 degrees. And now let's say we look at this configuration here. I have a straight line at the edge of my big square. I have the double tick mark here, the single tick mark here, and that means that the angle here has to be a right angle so that these 3 things add up to 180 degrees. So that tells me that my inner white shape has right angles in each of the corners. And then also by construction, right, each of these edges of it is a copy of the hypotenuse of my original triangle. So these are a bunch of things of length little c. So now let's take this same square and cut it up again. So what I'm going to do is I'm going to take my 4 copies of the right triangle, and I'm going to stack them together hypotenuse to hypotenuse like that. So I get little rectangles that are these rectangles are B by A or A by B rectangles. And if I stack them like this gives me a pair of squares. One of them has side little a, and the other has side little b. And this whole shape is a big square of side length a plus b. Okay, to argue that we have actually a square, we need to do various things with the alternate interior angles to justify that all these angles are right angles. Right, but that's a pretty straightforward exercise. So now let's look at these two decompositions. This is the one we started with, the first decomposition. Here is the second decomposition. They are two decompositions of the exact same square, right? We took a square of side a plus b and we composed it in two different ways. So the total area of this thing on the left equals the total area of the thing on the right. And by additivity of area, that means the area of the thing on the left minus the area of my four triangles is the same as the area of the thing on the right minus the area of the four triangles. And that means that what's left, so this white square on the left, has area that's the sum of the areas of the two white squares on the right. And now using the fact that the area of the square is just its side length squared, on the left I get c squared, and on the right I get a squared plus b squared. Okay, that's it for this proof. I think this proof is a really pretty proof in that you can explain it to anybody. It's visually a very compelling argument. I even saw it on a t-shirt once, admittedly a very mathematically themed t-shirt, but it's something that you can present without even any of the words, and if you think about it for a little bit, you can flesh out the proof. Next week, we will see my absolute favorite proof of the Pythagorean theorem. It's going to be less pretty to look at, but it'll be conceptually really pleasing. Okay, that's it for this video. Thank you for watching. I hope you enjoyed it. See you on the next one. Happy mathing.